Good afternoon, everyone. My name is Santosh Saini, and I will be moderating this session today. I hope I'm audible and can all hear us. If you are not able to hear me, you can type in yes or no in chat box, and accordingly we'll do that. So I guess everything is in order, and so a warm welcome to you all for joining us to this exciting webinar on. This webinar is part of the ICC CoolTech Webinar Series, and it is second. In this series, we will explore diverse topics related to the HVACR technologies, various fundamental and advancements in the HVACR technologies related to the cooling, heating, heat, waste heat, etc. So today we are privileged to have our distinguished industry experts who will share their profound insights on heat pump applications and potential market growth in India. So in this webinar, we have three speakers. Each speaker will present for 25 minutes, and following their presentations, we will delve into the question and answer session uh, and foster thought-provoking discussion to engage you all. Feel free to raise your questions using the chat box throughout the presentations, and we will address as many as possible questions in the end of the presentations, like in the question and answer session. So now let me introduce our esteemed speakers. So our first speaker is Mr. Rahul Pathak. He is manager and in product marketing and key accounts at Copeland India Private Limited. Mr. Rahul has experience of 15 plus years in marketing and business development. He is a mechanical engineer by training and has done MBA in marketing. He currently leads air conditioning and heating marketing verticals at Copeland. Today, he will guide us through the introduction to heat pumps, covering various types of technologies and their pivotal role in decarbonizing the heating industry. Our next speaker is Mr. Hemant G Dixit. He is a general manager at emerging technologies at Armstrong International. They works in intelligent solutions in steam, air, and hot water. Mr. Hemant has 20 years of experience and accomplished executive known for his strength in strategy development, sales, and marketing. As the general manager at Armstrong International, he will enlighten us on diverse applications of heat pump in India. Our next speaker is Mr. Professor Mohanraj Murugesan. Is a refrigerant and energy consultant at Heat Pump Research Institute, and he is also serving as a professor at Mechanical Engineering Department at Hindustan College of Engineering and Technology. Professor Mohan Raj is a seasoned refrigerant and energy consultant, bring his vast research experience at our webinar, specialized in environment-friendly refrigerants and heat pump technologies. He will present on various drivers and challenges in the adoption of heat pumps globally and within the Indian context. He will also discuss the suitability of refrigerants in the heat pumps and refrigerant transition caused due to various regulations worldwide. So in this session, the various topics will be covered by the experts are like general understanding of heat pumps, applications and required temperature for various applications in industry, in domestic and in commercial use. How to integrate the industrial the industrial heat pumps and the electrification of heat, as well as the industrial waste heat utilization, drivers and challenges in heat pump adoption, global policies, refrigerant transition, research and recent advancement in the technology of the heat pumps are the few topics which will be covered by our experts. So we already have like 109 participants have joined us, and I request Mr. Rahul Pathak to share his presentation and start with the. So, Mr. Rahul, over to you.
Uh,
I hope you can
Thanks.
share your presentation.
Yes.
Uh, yeah.
I won't. I can't see the share option over here. So if
So
someone can share
let
the
me check.
presentation.
Yeah, one sec. So Rahulji, now we check and I hope it is working.
Yes, I can share my presentation now. Thank you.
Sure.
All right. So thank you, Santoshi, for giving us an opportunity to interact with the industry stakeholders, particularly on the heat pump. So thank you for that. I really look forward for a healthy discussion on the introduction of the heat pump, and it will be followed by some interesting topics from other speakers also. So,
Rahulji, sorry for interruption. Can you please also switch on your camera
yeah,
if you are
one
comfortable? Yeah.
1 minute. Is it okay now?
Perfect, Rahulji. Thank
All
you.
right. All right. So, I was talking to AEEE for last couple of weeks in terms of what should be the the ideal topic for this session, and they came up with some 2 3 options, and finally as a team we decided to kind of go for 3 options, 3 different topics on the heat pump, mainly starting with the introduction, then the overall market sizing and the advancement. So I think the flow has been phenomenal. I think AEEE has done a good job in terms of ensuring that the most of the points related to heat pump has been covered. So with this short brief, let me start the today's topic, so which I am supposed to cover is the brief introduction of the heat pump technology, right? Now, if you see the overall audience today, I'm not sure the mix of the audience, but I believe, most of us are familiar with the heat pump, but if some of them are not, then it would be a good idea to kind of bring all of them in the on the same platform. So with that assumption, I will touch upon some basics of the heat pump technology. Excuse me in case if it is too basic for some of the people, but would be a good idea to kind of bring all the people on the same page. All right. So but the before we start the actual working principle of the heat pump, there are predominantly 2 types of heat pumps which are used in the market. One is the heat pump for the space heating, right? And the second is the heat pump for the sanitary water heating. That's the basic difference between these 2 types of usage as far as heat pump is concerned. So today we will concentrate on the sanitary water heating portion of heat pump, where this hot water used for the bathing purpose or any type of the sanitary usage, right? You can use it for the washing of your utensils, washing of your clothes, right? So anything related to the sanitary usage, this heat pump is used. Now, if you see the left hand side of this particular chart, there are 2 portion of the heat pump, right? Let me use my pointer. So there are actually the 2 portions of this heat pump. The left hand side is the storage tank where the heated water is stored, and the right hand side is the actual heat pump unit, right? And it typically has all the 4 key components, including compressors, condensing evaporator, and the thermal expansion valve. Now, what heat pump does is the job of heat pump is to kind of extract the heat from ambient, right? So through evaporator, the heat pump absorb the heat which is there in the ambient, and it is transferred to the water through the condenser coils, right? So that's the job of any heat pump. Extract the heat from the ambient, transfer it to the condenser coils, and then eventually to the water, right? And it happens through the refrigerant. So refrigerant is the medium to transfer this heat from the ambient to the water through these heat exchangers, right? And of course, compressor plays an important role to kind of ensure your vapor compression cycle is on, right? All right. Now, many of us have, talked about the COP, worked upon the COP or a ER of any system. Right? COP is nothing but the output of your system. So in case of heat pump, it would be output of heat pump in kilowatt divided by the input power. Right? So when I say the heat pump has a COP of 3.5 or 4, that means if I give 1 kilowatt of input to a heat pump, I get around 3.5 to 4 kilowatt of heating capacity. Right? So that is called the COP of any system. Whereas in electrical heating or the combustion type or like boilers and all that, the COP is less than your input power because of the losses involved, right? Like for example, it is less than 1, say 0.9 or 0.8. For 1 kilowatt of input power in electrical heating, you get 0.8 or 0.9 of heating capacity, right? Now, the reason behind having the higher capacity in a heat pump is around 70 to 75% of the heat is extracted from the ambient, and only the 20 or 25% of the heat is generated with the power fed to a compressor, right? So that's the reason the COP of a heat pump is always on a higher side, typically in the range of 2.5 to 4, compared to the conventional way of heating, like electrical heating or the boilers. Now you can see on the top, this is a typical installation of a heat pump. So you can see a heat pump over here, and this is connected to a mixing tank, right? Now this arrangement can be different based on the space availability and the project infrastructure. But typically this is how the installation looks like as far as the heat pump and mixing water tank is concerned. Okay. All right. With this, there are different types of heat pumps. Okay, you can see around starting with the commercial heat pump. If so, there are air to water heat pump, then water to water heat pump, or air to air. Air to air is actually a space heating, right? Now there are water to water heat pumps are also available. Now, if we go back to this chart, now what I said is heat is extracted from air and it is delivered to water with the help of the heat exchangers. So it is air to water heat pump, right? If I use a water chiller, right, and if I extract the heat from the water and transfer this to the water which I want to use for the sanitary purpose, then this case, the type of heat pumps would be a water to water heat. Right? So likewise, predominantly these are the three types of heat pumps: air to water, water to water, air to water. And depending upon the combination of water tank and the heat pump unit, we can further differentiate this heat pump like split water or the split refrigerant or even the monoblock. Some of the smaller heat pump systems has the water tank integrated in the heat pump circuit itself. So you don't have to have a separate water tank and a separate heat pump in case of monoblock. But of course, these monoblock systems are available in a smaller system as of now. The third category is the industrial heat pump, where the water temperature is generally on a higher side, the range of around 75 to 95 degrees Celsius, typically used for the processes for the industry. right? And of course, this is a different ball game altogether, because the designs of these heat pumps are little different. The final usage is different. It's not for the sanitary water heating. But yeah, I mean, this is the third category as far as the end usage of heat pump is concerned. This is industrial heat pumps, right? And the fourth one is the heat pumps used for the swimming pool. You know, with the increasing luxury style of the Indian culture, many of the hotel industry have started asking for heat pump, which can maintain the swimming pool temperature somewhere around 28 to 33 or 34 degrees Celsius, which is, comfortable temperature for any swimmer, right? So that's the fourth type of heat pump you can see in the market. Now, remember I said, you have to have a proper integration of your heat pump system with the mixing tank, and that defines the, the actual operation of your heat pump. And this will come up with the, your system integrators experience in the field, because depending upon the load, depending upon the quantity of water, the usage pattern of hot water, he decides the right combination of your heat pump and what size of mixing tank should be used along with the heat pump. So right size of your heat pump and right size of your mixing tank is absolutely important before the installation. And there, you need to have a, experienced system integrator to do this job, right? Now, to take an example, like if I use a 100 LPH heat pump, which is 100 liter per hour, that means in 1 hour, this heat pump is capable to give you 100 liter of heated water of 55 to 60 degree water, right? Now, if I kind of connect this to a 300 liter water tank, that means in 3 hours, heat pump would be able to deliver the 300 liter of water to the end customer, right? So this is a more of a faster heating example. But in case that project doesn't need that kind of a faster heating, it has a lot of time available. He's not in a hurry to kind of get that hot water required for his sanitary usage. He can club this 100 LPH with 500 liter tank instead of 300 liters. So he can get around 500 liter of water in 5 years to meet his requirements. So it all depends upon what end user needs. And based on that, we can always have optimum combination of your heat pump system and the mixing tank, right? You can see some of the examples of the installation for residential heat pump. I'm not going to talk about the commercial heat pump. The same logic applies over here. See some of the installation for the hotel and the hospital industry. We call it as a commercial heat pump segment. And the third one is the swimming pool heat pump. So you have a swimming pool over here and all the standard schematic, right from filter, drain. You need to have a sand separator for all your swimming pool. This is mandatory. Then sterilization happens because this is a chlorinated water. And then this water is fed to the condenser area of your heat pump, right? So there are tandem heat pumps which are used over here. And then the heated water is again supplied back to the pool, right? This is how the schematic looks like for swimming pool. Now, again, as I said earlier, this is a chlorinated water, so you have to have a a specialized condenser to handle this chlorinated water. Otherwise, corrosion may happen. So it may damage your the internal grooves of your condenser. It's necessary to have a specialized condenser while using heat pump for the swimming pool application. All right. Now, there are few things as an end customer, as an industry stakeholder, one should always look for, right? And because there are a lot of heat pumps available in the market, but there are few checkpoints one should look for. One is the right compressor, whether the heat pump is installed with the right compressor or not, right? Because many times, as an industry player, we have seen heat pumps are launched with a normal air conditioning compressor, which is not a good thing for end customer from the reliability point of view, right? I'll give you an example, from a layman perspective. Now take an example of, say, a normal air conditioning. Of course, this is a heating air conditioning, not the cooling, where the outside temperature is -7, and you want to kind of maintain the inside temperature around 20 degrees Celsius, right? So naturally, you have to have delta of 15 to 20 degrees Celsius. In that case, the condensing temperature of your heat pump would be around 40 degrees Celsius. So the amount of work the compressor has to do, right? So this in layman language, I say the amount of work the compressor has to do to maintain your 20 degrees Celsius when the outside is -7 is less compared to the amount of work compressor has to do in a heat pump kind of application. Now take an example of, again, around -12 in outdoor. So instead of 20 degrees Celsius, since it's a heat pump where you want to kind of maintain your water temperature at 50, with a delta of 5, your condensing temperature should be around 55 degrees Celsius. So naturally, from -7 to 40, compressor has to achieve from -12 to 55 degrees Celsius. So this is for compressor point of view, this is the worst condition, right? Now to accommodate this, wider requirement, you need to have a specialized compressor which has the wider envelope to kind of cater this particular requirement, right? So if you try to kind of use a normal standard compressor in a heat pump kind of application, chances of compressor failure is on a higher side compared to a heat pump with a dedicated compressor inside the heat pump, right? Now, of course, if you want to have a standardized, the heat pump specific compressor, you need to kind of change few of the component. I'm not going to go into the details because the topic is different today. I don't want to kind of dwell too much on the compressor. But the message I want to set here is look for a heat pump having a specialized compressor inside it, right? Again, this is too technical, but just to give a message over here, like this is a specialized compressor over here, having an operating envelope of 70 degrees Celsius, right? So it can easily kind of give you around 62 degrees Celsius kind of a water. But if you have a compressor having the 55 or 60 degree condensing temperature, then it would be difficult for a heat pump system to deliver, the higher water temperature from the heat pump, right? So look for a standard compressor inside the heat pump. The specialized compressor inside the heat pump. All right. So apart from the compressor, there are few more components which are important from the function of a heat pump, right? One is the heat exchangers. I mean, the water heat exchanger, particularly on the condenser side, where you exchange the heat from a refrigerant and pass on this heat to the water, which you save it in a separate tank. Now, there are different types of condensers available, right? Like shell and tube and then tube in tube. People are talking about the VSIT, which is a cost-effective version of your tube in tube, right? And even the efficiency also slightly goes up with the VSIT compared to a tube in tube. Even the weight of the heat pump goes down compared to tube in tube. But all in all, these are some of the types of condenser which are being used today in the sanitary heat pump market. Now, of course, this is based on the final usage of a heat pump. For example, heat pump is installed in a space where the water quality is not good, right? In that case, we always recommend, or the industry always recommend, to use a shell and heat pump with a shell and tube heat exchanger or a condenser, because if the water quality is not good, then the chances of developing a scaling inside the condenser goes up. So you need to kind of periodically, wash that scaling, which is possible with a shell and tube and not in a tube and tube. So wherever you have a problem with the quality of the water, we always recommend for a shell and tube condenser. And of course, where the quality is good, you have a 100% of your water supply from your corporation, then we recommend to go for a tube in tube. Of course, the cost of the heat pump with the tube in tube is little on a lower side compared to a shell and tube fitted heat pump. Controller, again, different types based on the make of the heat pump. They go for the PCB based or the branded controller, or even the PLC controllers so people have started using it. And on the defrost mechanism, defrost is, you must have seen in the domestic refrigerator of defrost mechanism. The same applies over here. When the ambient goes to 2 degrees, 0 degree, -2, -3, chances of accumulating ice on your evaporator goes up, right? And it affects the overall function of your heat pump. The efficiency of the heat pump also goes down. So to get rid of that, people used to give electrical heaters earlier. Slowly it got shifted to hot gas bypass because electrical heaters are the energy guzzlers, right? So the main purpose of using a heat pump is kind of, move away from a energy guzzler electrical heaters kind of a component. So industry understood that, and that moved away electrical heaters to a hot gas bypass. And then most of now the OEMs have started supplying the four-way valve, which is again a more efficient way of handling the defrost mechanism compared to a hot gas bypass system. Right. So these are some of the key components which actually are part of the heat pumps. Now, there has been a talk for many years, particularly when the heat pump got introduced, whether the solar is a good option, whether a heat pump alone is a good option. But taking the advantages of both the technology, whether it's a heat pump or whether it is solar, what we tried as an industry player is we have encouraged to opt for the hybrid systems whenever we have seen the solar system. The problem with the solar system, what we have observed is, since they have limitations of working, particularly in a rainy season or when the water usage is done in a day's time, and if end customer want the hot water in the night, there is no mechanism to kind of get the hot water if sufficient water is not stored in a hot water tank or a storage tank. So in that case, solar OEMs used to kind of offer these solar heaters backed up with electrical coils, which is not a good thing, from an energy point of view. So we observed that, the industry observed that and started supplying heat pump as a backup instead of electrical coils, right? So in this case, your primary source of getting the hot water is still from the solar, but for some reason, if you're not able to get the hot water from your solar, then heat pump can become your secondary system, right? So instead of using electrical coils, what we are saying is use the energy efficient option rather than using electrical coils. And then we have done many case studies. One of the case study is one hostel. I think it was, if I'm not wrong, it was in Pune. So they were using around 6 solar system, 500 LPD capacity, and they were using around 3 electrical backups, each 6 kilowatt. So we did that comparison. Our engineers were there and did this nice comparison of a solar water heating versus the heat pump. We replaced the entire solar water heating, which was backed up with electrical coils, with the heat pump. You can see this second installation over here. So this got replaced with the entire heat pump. And the kind of energy cost per day, energy saving which we have got, look at this, 756 versus 2592. I'll not go into the details. I'll share this with all of you later on. But the point I'm trying to make here is solar water heating with the electrical backup is not a good idea, but solar water heating with either you replace the entire solar water heating with the heat pump, or at least solar water heating backed up with the heat pump is a better idea rather than going for a solar water heating itself. Right? Even from the ROI point of view, you can see the around capital investment cost for the heat pump versus what you achieve on an annual year. The ROI is close to around 1.5 years. Right? All right, quick benefits. I think need not have to tell this, but as I said, around 3.5 to 4 is the COP, whereas on electrical heating, the solar with electrical backup, all of them are less than 1 COP. So that's the kind of difference it makes if you use a heat pump compared to a conventional way of heating. Right. I have a couple of more charts which talks about some of the advancement industry has done in the heat pump technology. Right. I talked about the shell and tube heat exchanger. Right. It actually helps us to kind of deal with the low grade quality of your intake water. That's point one. Specialized compressor we talked about. So it's very important to look for a specialized compressor for a heat pump. Integrated tank. This is again a new trend that we have seen where you have like 4 BHK, 5 bungalows, 4 BHK, 5 BHK kind of a bungalows and villas. People are, either going for a split type of a heat pump or the integrated tank heat pump. Right? You can see this is the monoblock kind of a system where the upper side is the actually heat pump fitted with a compressor, the heat exchanger, coil, everything. This is the controller. And the lower portion is the integrated tank of say 100 liter, 50 liter, 150 liter based on the requirement. All right. And again, 3.5 to 4 COP designated heat pump. So generally the heat pumps are available in the range of 3.5 to 4. Defrost system also we talked about. So many of the latest heat pumps are now available with the 4-way valve. So look for the 4-way valve defrost system in a heat pump. This is interesting. Inbuilt motor for a return line. I think most of us, have stayed in both, segments of a hotel, like, 2-star kind of a hotel and hotel like, Taj Hotel or, Leela Hotel of 5-star or 7-star category. One difference we have seen as the end customer is if you go to a washroom in a normal hotel, right? You have to wait for 2 or 3 minutes or 4 minutes to get the actual hot water inside your water bucket, right? But in 5-star kind of a premises, 5-star kind of a hotel properties, you get instant hot water in the bathroom. The reason is the return line, right? So in 5-star category of the hotel, they actually put one more return line from the upper water tank to your, washrooms. So in case, if your return line has the lower temperature, it has a solenoid valve. And so the job of that solenoid valve is to ensure at any point of time during the day or during the night, even the water inside the, tubes from water tank to, to your washroom is at the set temperature, right? So no matter what, at what point of time you open your geyser, open your tap, you will always get the hot water if you have a return line installed in your property. So these kind of nitty-gritties you have to check through the right system integrator who is plumbing specialist, apart from the HVC specialty from the heat pump point of view. But some of these things has to be checked before you actually install the heat pump in your property. Again, look for a locally designed build systems, because these locally designed systems are made for, Indian climate conditions. I've seen many of the heat pumps are bought with the imported systems. Those designs are made for their country, not for Indian countries, right? It's India kind of a ambient condition. So always look for a locally designed systems which has capability of handling the India ambient conditions. Intelligent system control, again, a very important point because if something goes wrong inside the heat pump, the service team should be able to decode the problem inside your heat pump, which has the diagnosis and troubleshooting protocol inside the controller. So those are some of the advantages you get with the right type of control inside your system. Okay. And last but not least, for the pool heat pump, as I said earlier, that it should have the special condenser, which is actually a titanium tube condenser. which has the capability to handle the chlorinated water. Right? So these are some of the advancement we have seen from last couple of years in the market. So thought of by sharing this advancement apart from the basics of the heat pumps into this session. With that, this is what I wanted to kind of pass on to all the attendees today. So back to Santosh.
Thanks, Rahul, for this wonderful presentation. I request our next speaker, Mr. Hemant, to present their slides and yeah. So, Riya, presentation.
Hi, good afternoon to all. Good afternoon, good morning, good evening, whomsoever actually joined from whichever the location. Let me actually thanks. First of all, thank you very much for AEEE for giving this opportunity to present behalf of the AEEE on the Armstrong product, so the solutions as well as actually diverse application. I hope, am I audible to you all?
Yes, Hemant Ji, you are perfectly audible.
And is my slides are visible?
Yes, now it is visible.
Okay, thank you very much. So before going to the today's actually the topic, let me take 2 more minutes to introduce about myself as well as the Armstrong. Okay, myself Hemant Dixit. I'm the general manager. Already Santosh has mentioned on this. I take care about the emerging technology for Armstrong International, India and Southeast Asia. And okay, just to actually not take 2 slides about the Armstrong, who we are. It is 123 years old company set up in 1900 by Adam Armstrong, privately owned and managed by the 5th generation of the Armstrong and the Blass family, having more than 60 countries presence, 15 plus global manufacturing facilities, almost 3,000 plus employees are working across all the 15 factories. We are the global leader in steam, air, and hot water. When it comes to steam, many of the people who are already using the boilers and all other things, they will be aware about the inverted bucket steam trap, but they might not be knowing this inverted bucket steam trap has invented by Armstrong exactly 113 years back. Started as a steam trap company, now we are the thermal expert. The same way, we are one of the largest manufacturer of humidifiers and wireless trap monitoring systems, cloud-based utility monitorings, and all other things. So as we said, we are the complete solution provider on this. These all are the 15 facilities of the factories, what actually I mentioned on the overall. And we are just not actually the equipment suppliers. We give the complete engineering solutions, which talks about the on-site optimization study, customized design, optimized thermal efficiency and the flexibility studies, integrated packages, trunk implementations, and not only that, we do the even whatever the given commitment, we do the measurable savings as a single point of responsibility. With that, directly I will jump on to the today's topic of the diverse application of heat pumps, that is the heat recovery in the light industries with the help of circular thermal. Today we hear a lot actually because already Rahul has mentioned about the heat pump, the basics and all other things, the couple of applications. So today actually we are hearing a lot about the challenges of decarbonization in the low temperature industrial heat because of the government policies, because of the Fortune 500 companies, the decarbonization or the net zero initiation. And why all those things are coming, we need to understand first. And as we all know, industrial heat represents more than 10% of the greenhouse gas emissions. And out of that, the major is actually coming from the heavy industries like steel, cement, refineries, and all. That mainly requires the high temperature heat. And in today's topic, we are not going to cover much about that. It is responsible for the major significant part of the thermal emissions, but in the same way, even low temperature heat, like less than 120 degrees C and all other things also represent almost 31% of the industrial heat demand. And mainly these 31% of the industrial heat demand comes from the industries like food and beverages, pharmaceuticals, FMCGs, light chemicals, and automobiles and all other industries. And for these industries, what should be our approach and how we can achieve this net zero or the decarbonization for these industries are mainly on the optimization, minimization study, as well as the de-steaming to complete the decarbonizations. So what the optimization? The optimize the total efficiency of the thermal network, because we all know that any thermal network will have the generation, distribution, utilization, and the recoveries and all other things. When we need to optimize, we need to give the complete holistic approach on all these four components or the four part of the thermal network. It will include even recovering all the waste heat wherever it is possible. Once that is through, then we need to come to the next thing that is called the minimizations. Minimize the process demand, even if it requires even changing the equipment with high efficiency equipments and all other things, or even lowering the set point wherever it possible. So next is the ones actually we through with optimization and minimization. Next should be our target should be the de-steaming to complete the decarbonization, so that we can the remaining thermal generation of the low temperatures, we can de-steam it on this. And what it requires to do that is the thermal networks needs to be much more flexible to handle the multiple inputs like source versus the sink. So this is what actually requires. If you see the thermal decarbonization possibilities in the different industries, like starting from ice cream to the coffee, like waste soft beverages, breweries, other food industries, household product like FMCGs, pharmas and all these industries have the different percentage of potential on the different areas like minimization, optimization, or decarbonization by the de-steamings and all. If we take the ice cream in the ice cream industries, the optimization will actually give the major percentage, major actual chance of actually the savings. But same way the beverages, breweries and all having the equal opportunities with the minimization, optimization and de-steaming things. And the coffee, we can get a more benefit even by de-steaming rather than actually putting more effort on the minimizations. So like that, it changes from industry to industries, and we should focus for each industries customized to give the right solution for that. And we all know that the current thermal systems, because today's topic is on the more on the heat pump and the hot water. So if you see the current thermal system, which includes the generation of the hot water with the help of steam boilers, and the steam boilers will be run with the help of fossil fuels. That is what is all the conventional thermal system actually works. And if you give 1000 kilowatt as an input to this thermal system or the steam system, almost 20% of the energy will be lost in the boiler house itself. It might be in the stack loss, or it might be like enthalpies or the radiations, blowdown losses and all other losses. Almost 20% of the energy will be get lost in the boiler house itself. So remaining 80% will comes to the process. Like in the 1000 kilowatt of the equivalent of the fossil fuel, only 800 kilowatt will be coming to your process. In typical example, if you take a dryers, if you have to dry something, when you are drying, that means we are taking out that moisture content in that product. So, and that will actually go along with the stack. So almost out of the 100% actually the energy, when it comes to 80%, out of 80%, 60% or actually approximately 60% will go or will carry in the stack itself because of this drying effect. And that is a process. Okay, and only approximately 10% will only get carried to the product, and remaining actually 8 to 10% will be like a radiation losses. So the effective of the 100%, the 60 is the one which is the real work, and remaining is actually which anyway it is unaccountable, or in the same way it is unavoidable. And because of this decarbonization initiation from the different agencies and all other things, gradually what happened, the fossil fuel has replaced with the renewable energies, same as biogas and hydrogen, even followed with the solars and all other things. But this thermal system remains same. Only the changes happened is instead of the fossil fuel, these things actually shift has happened on the renewable energy portions or the biogas and the hydrogen. The next step actually what came is after this decarbonization or the renewable energy, the next thing came is like a de-steaming of the effect. So what the industry did is, instead of actually generating the steam, then converting into hot water, then using that hot water for the process and all other things. So industry started, or actually we all actually because started recommending them to de-steam itself, so that the boiler has gone in place of the boiler, direct hot water generators came in between. So it's the same with the help of same renewable electricities, biogas and all other things. So that earlier, whatever the 1000 kilowatt was the input, that got reduced approximately 18 to 20%. So almost 800 plus kilowatt is only the input required to the thermal generators now. That will continue to the production side or the process side. And what is the real thing is, when we all know that almost 60% of the energy is going to get lost as a part of the process to the atmosphere, why to waste that? Why can't we capture it back? And that phenomena or that process is called the circular thermal system. And instead of wasting that, let us recapture that. And let us recapture and reuse that system, so that if we are actually getting it the 600 kilowatt back, then the real energy or the fresh energy is required is only 200 kilowatt. And this can be done with the proper industrial heat pump. And industrial heat pumps are available in the different actually, the categories. As already Mr. Rahul has mentioned, even in the industrial side, heat pumps are available from 40 degree to 120 degrees. And in Armstrong, we have the 3 range of the actually, because always we call the 3 tier or the 3 range of heat pumps, like the low temperature up to 65 to 70 degree, medium temperature up to 90 degrees, and high temperature up to 120 degrees and all. So these industrial heat pumps are available in the all actually different categories. So using those industrial heat pump, we can recapture all the waste heat, which is the real energy saving. And waste heat not necessarily like a process waste heat. Waste heat actually can be anything. Now earlier we spoke only about the thermal or the heating. The same way in the same process industries, every process industry require the cooling also. And for example, why the chiller will be used? The chiller will be used to either cool the process or cool the space. So that is when it is coming, for example, if you take actually in a 12 degree chiller, the 12 degree will comes to the point of use, it will cool that area or the process, goes back. And when it is going back, it will be higher than the 7 degree or higher than the supply temperature. So that supply higher the temperature is nothing but a waste energy which is carried from this process. We all know that energy neither be generated nor be destroyed. So when actually, because if you have to transfer or if you have to cool the area here, this energy has to transfer for some other areas. And that is what the chiller network does. It takes the energy from here, or takes the waste energy from here, it puts back to the chiller, and from the chiller, it goes to the cooling tower. And that is the second point of actually energy. If this is not, the same thing will be actually get carried to in the cooling tower side. And that is called the waste heat. So the waste heat can be anything like the chilled water return or the cooling tower return, or even the consistent waste heat in any liquid, or even for the hot exhaust gas or the air. And in the heat pump, we can make use this as the source. End of the day, heat pump is nothing but it is the machine or the device which is actually going to take the energy from the source side, and it is going to put it on the sink side. Means the waste heat will make it as a usable heat. Okay, and to do that, it is very simple. But what exactly required? How this can be done? So if you take the typical any process industries, the process industries will have the many blocks or the many utility requirement areas and all other things, towers. I hope I'm audible, correct?
Yes.
Yeah, thank you. So like, for example, if you take this particular, it is having the block A, block B, block C, block D, and all other things. All these blocks are in the different locations. It is so whenever actually, because when we talk about using the circular thermal or recovering the heat and all other things, we need to do the proper study, which should cover heat source and heat sink analysis. What is the source available? What is the sink required? And how we can synchronize these two things. To do that, the physical location of the plant is very important. The first and the foremost is we need to understand the proper physical location of the plant, then timing of the demand and the supply, followed with the level of temperature variations and the level of load variations or the amount of heat required. Once we understand those things, then it is going to give us idea about the is any thermal storage balancing is required. For example, if the timing of the demand and supplies are varying, then automatically then we need to do the thermal storage balancing, whether it might be like a stratification buffer tanks or even having the simple hydronic separations. Once we recover the heat recovery should not necessarily with the heat pump. Heat recovery can be done in any form. And once actually, because it gives the idea saying that actually exactly the heat pump has to be done, then the next level of analysis has to go followed with the which is the source and how it has to be balanced. If the source is insufficient, do you have any cooling energy available on the other sites or the nearby within the same plant? Or like a chiller network and all. Not necessarily even the chiller or the waste heat. Even all the industries will have the air compressors. So then we have to study the even number of compressors availabilities and all other things. So that can we use those energies which is actually getting lost to the atmosphere. So heat recovery will not have any limitations. Wherever any waste heats are available, we can capture those waste heat, we can put it back to the usable heat. For example, in the same location, like ABCD, what I mentioned, the blocks. For a simple example, let us see the A block is having the waste heat of almost 110 degrees. So, and the B block is having the 168 degrees C, and the C and D having 113, 190 and all. Typically, what we do is, to avoid the complexity of the network and all other things, we do the localized heat recoveries. Like A block, okay, even if it is 110 is there, let us actually heat up to whatever the possibilities. And the B block, if it is a 168, even though it is very high heat, still the sinks are actually the usable applications are low. Still you try to use those heat within that. But is it right? That is what always we need to think. Is the degrading of the heat from 168 to 34, is it relevant? Will it make sense? Those things always actually we need to analyze. For example, this is what actually I mentioned, having 110 to 96 heating A, B will happen 168 to 34, C block might happen 113 to 113 and all. So we need to understand, is it really makes sense? And this is where the expert actually come into the picture. We need to do the proper pinch analysis of this plant. By doing the pinch analysis, we can actually come to know where exactly the location, which heat has to be used where, so that we can minimize the complete fresh energy requirement itself in the plant. Always it has to be from higher to the lower. For example, if you see the source or the heat hot stream is highest is actually D, which is having the 190 degree here, and the lowest is the A, which is having only 110. So always it has to be in this order. So which is the highest should come first, then followed with the next one. Same heat recovery should be actually, because whichever is requires higher and whichever required. So those has to be combined. By doing that, we can recover the maximum amount of the heat which is going to get lost, or we can recover the maximum amount of the waste heat which is getting lost to the atmosphere. That will even help to reduce the overall energy requirement of the plant. And for that, the pinch analysis always gives the right idea how it can be done. So which is going to give you the hot stream and the cold stream graphs, then you can have the composite curve, which will actually give you where the pinch point will come into the picture. And always, wherever it is not possible, like a lowest energy which cannot be recovered, that should be used for the heat pump to put it back to the highest energy. So that these two pockets are always unapproachable with the normal heat recovery. So these heat pump should be used for this area so that we can do the complete heat recovery of the plant. So by doing the pinch analysis, which will help us to identify the optimum heat exchangers network between the hot and the cold stream to minimize the energy requirements. And also it will help us to determine the where exactly heat pump has to be put. And just actually we mentioned about the pinch point and all other things. So the pinch point is an imaginary point. The pinch point is the location in the heat exchanger where the temperature difference between the hot and cold fluid is minimum. So that point is called the pinch point in the pinch analysis. And whenever we are doing this pinch analysis, there are actually a couple of rules, and a very simple rule is, if let us assume that actually whatever the pinch point or the pinch line we set, always energy should not be crossed each other. For example, this should not, the heats which is above the pinch point should not come to the below the pinch point. Like 100 should not be used for the 20 or the 40. Same way 80 should not be used for the 40 or the 20s and all other things. And always it has to be recovered in such a manner that highest will be used to the highest and lowest will be for the lowest. So that by doing that, we will avoid the greater extent of the energy requirement in the plant. So this is what is about the circular thermal, and this is what is the proper way of doing the pinch and how it can support us to optimize the energy requirement in the plant. With that, let us move to the couple of applications of the heat pump. And if you go to this, typically in food industries, almost 60 to 70% of the hot water requirement is for the wash down or the sanitary applications. The same way in almost majority of the injectables and all other pharmas, high-end pharmas, the majority of the hot water requirement is for the AHU applications. And the third industry, like what I mentioned, was the automobile. Even there, majority of the steam consumption or the hot water requirement is for the paint shops. And all these things are the low grade heat or the low temperature heat. And one more thing is, all these industries, whatever you mentioned, have the simultaneous heating as well as the cooling. For those coolings, typically the chiller will be used for the cooling applications. And that is what actually the function of the chiller. And heating will be done with the help of remaining source like either the hot water generator or the steam boilers and all other things. Instead of using the steam or instead of using the hot water generator, we can have the heat pump itself directly. So by having the heat pump, which will give you the direct heat to the heating coils or the heating application, so that you can avoid the steam consumption or the fossil fuel consumption. Not only that, for this water to water heat pump, source is from, for this application, source is from the chiller network. So that when actually we are using the chiller energy or the chiller return energy as the source for this water to water heat pump, automatically that is going to reduce the load on the chiller. So that means what? We can minimize or we can cut down the chiller requirement itself. So that by having this, which is going to save you in terms of the steam consumption, not only that, even it will reduce the power consumption or the electric consumption for the electricity requirement for the chiller side also. So by having the water to water heat pump, we can have the both benefits. For example, in the given in this one, this plant requires almost 400 TR of the cooling load for the process heating, for the space heatings and all other things like AHU heating and all other things. Simultaneously requires almost 560 kilowatt of the hot water requirement or the thermal requirement or the heat requirement. So by having the heat pump, now what is going to happen in the chiller side? The chiller side, 7 degree from the 7 degree C of the chilled water is coming to the process to do the work. And while going back, it will be near to the, because design is 7/12. So it will be near to the 12 degree and goes back once again. The chiller will cool it back. So this is what is the circle. It will always keep on happening. Now having the heat pump can actually take the energy from here itself, return line itself, return water which is coming at 12 degrees. And this will become like a source for the heat pump application. By having this source, you can get a 560 kilowatt. To get a 560 kilowatt, approximately, you might require 180 to 185 kilowatt of the electricity energy. But in the same time, you will get 560 kilowatt on the condenser side or the hot water side, as well as the 370 kilowatt or the 105 TR on the evaporator. So the thing is, it will pre-cool or it will give the pre-chilling of the 105 TR. Because of that, now the water which is coming back is going to be less than 12 degree. Means that directly you can switch off the 100 TR of these machines, and not only 100 TR of the chiller load it will not reduce. Along with that, it is going to reduce even the cooling tower requirement, connected circulations and all other things. More than that, even it will avoid the water losses from the evaporation, drift, blowdown and all other things. So that is what is the benefit of having the water-to-water heat pump in place of the conventional hot water generators. So summarize this, what is going to happen is, even heat pump is also going to work as the chiller. So along with giving the chilling effect or the chiller load, it will also give the hot water. So you can have the hot water as well as the chilled water both simultaneously from the machine. So what does the heat pump do is, just to recapture, by taking the electricity as the energy input, it gives the heating as well as the cooling both. And not only that, along with that, it will help us to decarbonize the system so that it will reduce the CO2 emissions. And which all are the locations, which all are the places where we can do is, in generally, many process industries requires a simultaneous heating as well as the cooling. And wherever the simultaneous heating and cooling are required, there water-cooled or the water-to-water heat pump or water-sourced heat pump is the right application, which can give you the combined COP, means it can give you the two COPs. The COP is nothing but a coefficient of performance. So it will give you the COP on the heating side, and it also gives the COP on the chiller side or the cooling side. So the added COP is always going to be the higher than the any other heat pumps. And so that is the major advantage of water-to-water heat pumps than the air pump. And applications are many, starting from ice cream industries to the meat, breweries, dairy, canned food, pet products, even reactors, fine chemicals, autoclaves, AHUs, paint shops. You take any process industries, all these process industries will have the simultaneous heating as well as the cooling. Okay, so that's what actually we can make use. And not only that, even the, like actually earlier mentioned, the waste heat not only from the chiller or not only from the process, even waste heat we can get it from the air compressors. In the air compressor, there are two types. One is the air cooled, second is the water cooled. In the water cooled, generally what will happen, just to cool that the compressor, the water will be circulated and that water will comes back to the cooling tower and that will keep on cycle. That cycle will keep on happening. Instead of actually wasting that energy in the cooling tower, we can capture that heat. Even we can generate from the simple 36 degree of whatever the general it comes to the cooling tower. By using that heat, even we can generate up to 120 degrees C hot water. We can generate up to 120 degrees C or the 240 degree Fahrenheit hot water that can be used in any process. And the next application is like all the dryers. That's what we have shown in the circular thermal presentation, the slide in the previous. Normally, all these dryers, the exhaust air is always going to be higher than the atmospheric temperature. So it will vary from 50 to 80 degrees and all other things. Instead of giving this hot discharge, we can recover the heat of this exhaust air, and using that heat, we can even actually preheat the same air which is going inside the dryer, or even we can make use up to 120 degree of hot water in the different places, wherever actually we need the process applications. And the very actually typical and very easy applications in the boiler feed water preheating, because we all know that any boiler will be actually X capacity with the F&A 100. So that means from an at rating of the 100 degree. So always for the any feed water tank, the target is reaching to the 100 or actually exceeding to the 100. And to do that, the people will be what they will be using. They will be doing is they will be sometimes if the condensate recovery is not full or it is not up to the 100% of the thing. So then they will be actually directly purging or directly putting the steam, directly injecting the steam. Instead of injecting the steam, we can use the heat pump as the source, which can give the water up to 90 degree plus, or even for the 100 degrees and all other things in the feed water near to the 100 degrees. Okay. So that is what is the another actually, the applications for the heat pumps. And not only that, even with the heat pump, we can generate the low pressure steam, and using the steam compressor, that low pressure steam can be boosted to the medium pressure also. Heat pump can generate low pressure steam up to 120 degrees C of the temperature. And then subsequently, what are the requirement? It can be used with the help of MUR or the steam compressors. So heat pump application is very wide and very diversified. And wherever there is a waste heats are available, we can make use of that into the usable energy. So the application is not limited for any one or two things. And these all are the things, couple of actually small examples what we mentioned, but we need not to stick on to only these applications. Even wherever there is a waste, always we should think how it can be recovered, where it can be recovered, and what should be the solution for that. And in the hotel industries, like the majority of the actually the steam application is either in the laundry or for the bathing. And for the bathing, it always requires the 60 degree water just to keep the global guidelines intact. Like all the ashtrays and all actually always talks about maintaining the 60 degree in the tank to kill the Legionella and all. Heat pump is the right applications. With the help of heat pump of this, even the 65 degree things and all, easily you can maintain the constant 60 degree in the mixing tank. Then with the right proper application like a DSS and all, even still you can maintain the ASHRAE 188p standards and all other things. And there are many hotels like Marriott, Hilton, Leela and all, they got this benefit. So this is what is the different applications for the different industry segment and the different probabilities. And so this is
sorry for interrupting, but we are exceeding the time. So can you
yes,
please wrap
this
up?
This is the last slide.
Sure.
Yes, with that, it will actually gives the different applications and all other things. But in the same times, we should know the challenges of the heat pump also, because we heard a lot of actually pros of the heat pump. In the same way, we should remember one thing: heat pump is not instantaneous. So that is the reason whenever actually, because heat pump actually we design, and there is a lot of actually remark about the heat pump, but none of the machine will never fail. Any failure is going to happen, it is going to happen from the engineering side. So it is an engineering failure, not a machine failure. And why those failure will happen is if you don't take care about the proper thing on the source side as well as the sink side. And when it comes to the source side, always we should know what is the waste heat available and the water flow and all. And this requires always the consistent water flow or the constant water flows and all other things. If there is a variation, accordingly, we need to take it. Same way in the sink side also, we need to understand properly whether it's a continuous load or the batch load and all. Based on that, it has to be properly. For example, if you take 100 kilowatt is the source, with that actually 150 kilowatt is the heat recovery what you can do. With 100%, the people might have said actually COP3 or 3.5, whatever it is, it will give you somewhere in 2 years payback. In a simple example, I'm saying, if the source will decrease to 50 kilowatt, it cannot give you the 150, then it will become the 75. That machine is going to work at a less than 50%. Automatically, COP is also going to get down. So your payback and all other things will affect. So keeping all those things in the mind, proper study and proper feasibility is very important. Keeping that, I will wind up my today's presentation. Once again, thanks to AEEE as well as Santosh for giving this opportunity. This is our contact details. And with this, I will be over with actually our promise of providing an intelligent system solution that improves the utility performance, lower the energy consumption, and reduce the environmental emission while providing an enjoyable experience. Thank you. Thank you very much.
Thank you very much, Hemant Ji, for this informative and wonderful presentation. Without wasting time, I'll invite our next speaker, Professor Mohanraj, to start the presentation. And yeah, we have only like 15 minutes left, so please wrap up as early as possible so that we can have a question and answer session as well.
Yes,
Professor
yes, just a
Mohanraj.
minute. Yes, just a minute.
Yes.
I'm sharing the screen. Just a minute. Can you able to see my screen?
Not yet, sir.
So just a minute, sir. Screen share.
Yes, sir, we can see your slides.
Slides. Yeah. Sir, can I continue? Yes. Sir, my slides are visible?
Yes, slides visible, but can you turn it on presentation mode?
Yes, now it's okay, sir.
It is not started yet. I think you
see. I started in my laptop. I started.
Okay.
So now it's okay, sir.
So still in the same view, I think. I don't know. What's the issue?
Somewhere.
Sir, you need to.
Now it's okay, sir.
So you need to turn on the presenter mode, that is at the bottom of the page. You can see the percentage 83% at the bottom of the presentation, and on the immediate left to it, you might see a screen.
Yes. Now it's okay. Now it's okay.
Not yet.
See here, I started this one. This one I have to click.
Yes, exactly.
Yes, but in my laptop it was in a screen, so full screen mode.
Sir, you go ahead.
I think so. You should go ahead. I think there's some technical issue, but we are able to see the screen anyway.
Okay, can you able to see my screen?
Yes.
Okay, so good afternoon. So myself, I am Dr. Mohanraj. I'm going to give a presentation about the heat pump systems, the market potential and its challenges. So, I'm from Heat Pump Research Institute. So this is my own research institute. I am establishing this institute to explore some of my heat pump research for the society. So especially in the field of drying, water heating, heat regeneration purpose, and desalination purpose. So we have developed some heat pumps, which we are going to showcase in this presentation. And I also going to explore some of the market challenges and potential of the heat pumps, especially in the Indian scenario. So I'm going to give an overview of this heat pumps, as already two presenters that are giving a detailed information scope of applications of heat pump. In my view, I'm going to give a slightly deviate from that two presentations, but slightly deviations, but they are giving a detailed information, but I'm giving my own opinion only. So these heat pumps have been identified as an energy efficient heating device because the heating demand is very high requirement, especially for drying applications, water heating applications. Even in India, since it is a tropical country, we don't have a space heating demand, but in some parts of less than 20% of the locations we may have, locations in India may have some heating requirement for the month of 4 months, especially in some hill stations. In some north part of India, we may require some heating. To meet that heating requirements in such spaces in an energy efficient way, we may provide some space heating, and also for the greenhouse heating, especially in the case of drying applications for processing of some agricultural products, we may require some heating. But during the daytime, we will get from the solar energy. But for the continuous, consistent heating, we may require some energy efficient heating device during the night time. Yes.
Sorry, sir, for your slides are not changing actually.
Sir, slides are not changing.
Yeah.
Yeah, just some problem, sir. Just a minute, sir. I don't know what happened here. See. Can you able to see the slide, sir? Please.
Yes.
Slide changed. So slide now it is in second slide. So have you able to see this, sir? Second slide.
Yes.
Second slide. Now it's in presentation mode. It's okay.
Sir, we can still see in the previous format, but the slide is visible, so you might want to start.
So in this now it is in second slide.
Yes.
Okay. So I'm going to give a brief information about some scope of applications in my point of view. It may be for drying, water heating, space heating, as you already mentioned in the earlier slides. In extension to that, we have some applications in greenhouse heating. Greenhouse heating for during the daytime, we are heating using the energy, solar energy, but during night time, we can utilize some energy efficient heating systems like heat pumps. And we need a textile industries, we may require around a temperature of 70 to 80 degrees to maintain the quality of yarn. So for that application also we may require heat pumps, and for laundry applications is a very essential. And in some places they may require hot water. They're utilizing a boiler for producing the hot water for laundry applications. And even for some poultry applications, in some cold climatic conditions, they may require some comfortable temperature of around 30 to 35 degrees centigrade for poultry. They're also requiring some heating systems in heating demand. So even yesterday also I have suggested a heat pump heating system of around 100 kilowatt heating requirement using a heat pump. Using a 40 kilowatt, I suggested a 40 kilowatt semi-hermetically reciprocating type heat pump for such applications. And also for painting up booth applications for maintaining around 50 degrees centigrade. And also for desalination is a very big problem. In most of the thermal desalination systems, we require heat pumps to require the heat during the condensation, and it is utilized for preheating the saline water before entering into the thermal desalination units. And also for some heat recovery applications. So in many places, we may have large volume of heat is exhausted to the atmosphere. So this is a one method we can use it to recover the heat from such waste heat, and can be utilized for preheating the fluids for the requirements. So these are some of my the applications from my point of view. Because we are identifying this is an energy efficient heating device, because it is capable of delivering a more amount of heat than it is the work input. There's electricity input required for its operation. Okay, so this is some of the heat pump demand, heating demand in various industries. Can you able to see this slide number 3? Excuse me, can you able to see the slide number 3?
No, sir.
So no. So now.
You have to move. Yes, visible now.
Now it's okay.
Yeah.
Okay, so now these are some of the applications of the heat pump for the applications of the heating demand. For the paper industries, we may require a temperature of around 100 degrees centigrade, and it may have a temperature 100 to 200 degrees centigrade. And for the food and beverage industries, chemical industries, automobile industries, and for some metallurgical applications, and for plastic molding. So these are some of the major industrial applications, in extension to the water heating applications for space heating and for the domestic requirements. So even for the textile industries, we may require a temperature up to 160 degrees centigrade for coloring and dyeing. So we may require. So for the wood processing industries also, for wood drying, they may require heating. And for several applications, several other applications like for washing, cleaning, and other miscellaneous applications, we may require hot water, which may be in the range between 50 to even 140 degrees centigrade. So to meet out all these requirements, the heat pumps currently available can meet up to the temperature of say 80 degrees centigrade. Suppose if we wanted heat pump, if we wanted heating demand of more than 100 degrees centigrade, there is no proper heat pump. It is available in the Indian market, but so most of the heat pumps we are not standardized. So moreover, this heat pump concept is not matured in India because of a lack of standardization and all. So we are in China. So we have more standardized heat pumps are available even to meet the requirement up to 120 degrees centigrade. But the current research progress is made and to produce the hot water at a temperature of around 150 to 150 degrees centigrade using some olefin refrigerants. So there is another problem. So there is no proper working fluid to meet the heating demand up to the temperature of 150 degrees centigrade. So these are some of the hurdles which I am going to present in the coming slides. So in India, so the heating the requirement is for the drying applications. First, we can talk about the drying applications like for drying of cardamom, drying of pepper, so drying of some cashew nuts, so drying of some costly dry fruits like that. We may require a temperature of around 60 to 80 degrees centigrade consistently throughout its drying process. So none of the conventional drying methods will not maintain the temperature and also to maintain an energy efficient. They are not having an energy efficient process. So this may leads to a lot of difficulty in processing this. So in such cases, maybe most of the electrical dryers are energy intensive because if you can give a 1 kilowatt means that will deliver only 0.8 kilowatt of heat output, whereas heat pump will deliver 3 times higher, minimum 3 times higher. So normally we can climb the COP of a heat pump around 2. In general, it will be 2.5. So it will be operating at minimum. At worst case, it will deliver a heat pump of COP of 2.5. In general, it can be operated to up to a maximum of 4. When the temperature changes, the temperature, if it is going in higher and higher, then the capacity loss will become, and it leads to the loss in COP. So in general, 40 degree temperature lift is the optimal temperature lift for a single stage heat pump. If we can go beyond that, there will be significant loss in heating capacity, which we came across with several studies. And also we have to go for the 2-stage heat pumps. That I will share it few informations in the coming slides. So now we are so now I move to the 4th slide. So what are the key factors influencing this global market? So that is the main thing is an energy efficiency. So because the heat pumps is an energy efficient device, and it is capable of delivering a more heat output than its energy input requirement. So we can, because of its higher energy efficiency, it may be getting an attractive option for heating applications, especially for drying, water heating. These are the major applications as far as Indian climatic condition is concerned. And in some part of locations, we may use it for space heating also, and some we can use it for even for desalination application also. So even a portable, we are also developed a portable desalination heat pumps, that heat pumps which can be integrated with some desalination applications for producing thermal desalination applications, and we came across with some succeed results. And another thing is then since the lot of heating demand requires more, we have to need to spend more amount of energy, which is the conventional energy resources, that makes it to more carbon emissions. This may be a major problem. So if we can focus on environmental conscious, then we can go for the heat pumps. Most of my studies, when we are done a lot of research and research activities in the field of heat pump, and that focuses, that results gave that approximately 70% to 80% of carbon emissions can be reduced if we can go for a heat pump. 70% if we can operate the heat pump in ambient source mode or in a solar source mode, or we can go for an integrate with some photovoltaic the evaporators, photovoltaic thermal hybrid evaporators. It is possible even up to 85% of carbon emissions can be reduced. Thereby, we can have significant environmental benefits for the heat pumps. So if we focus on this environment, this will be another another benefit to move towards these heat pump options, because because lack of awareness on these aspects, the people are not thinking to move towards this heat pump options. And the government subsidies, because of the lack of subsidies, the promotion of heat pumps is also will become less. Even if we considering promoting a solar photovoltaic panels, promoting a wind energy generation power plants, the government has given a lot of subsidies. Because of that, many big industries, they have installed the big power plants in many parts of the country and they're producing the required electricity, required power. So if we can promote this heat pump also for many applications, especially for drying applications, water heating, industrial applications, and also for some desalination applications, government has given some subsidies to promote this heat pump heating concept. So we may expect so the government should give some encouragement for going for this type of energy efficient technologies. And nowadays the heat pumps should have having some advanced technology, so which will focus on the according to the requirements. For example, if some ambient conditions, they may fluctuate between 20 to 30 degrees centigrade. So some ambient conditions, even some climate may have winter, they may have a temperature of 20 degree. Summer may they have a temperature of 40 degrees centigrade. Some smart technology should if we can recommend, we can use, that may have some. It may be, for example, if we can operate this evaporated temperature, can change accordingly according to the ambient conditions. So such type of mechanisms can be provided, can be automatically changed with the help of some automatic electronic expansion valves, which may be interfacing with an ambient condition. So according to the ambient condition, the temperature, evaporated temperature, can be automatically shifted from lower temperature to higher temperature, and they will maintain the operation according to the climatic conditions. So such type of advanced technology, such type of advanced information should be implemented, and it should be promoted to reach the customers to improve the heat pump demand in the country, and also for the multi-purpose technology. So we are planning to have the heat pumps to have 2-3 functions. For example, for air heating, air cooling, and also water heating, water cooling. So like that, we have some multi-purpose options should be provided. Even in China, the heat pumps are available with 3-4 functions. So 3-4 functions. So such type of multi-purpose functions are nowadays we're expecting in a single equipment. So such type of expectations, it should be fulfilled. And if you have a heat pump which multi-purpose function, that will be, you can promote very easily in the market. And the renewable energy integration is nowadays getting attention because it is possible to integrate the renewable energy resources like solar energy, solar photovoltaic thermal hybrid energy with the heat pump systems. Thereby we can get this we can provide a enough source to the evaporator, and it can be, and also if we can integrate a photovoltaic panels, means so that we can utilize the evaporator cooling for the for providing a cooling to the photovoltaic panel. Thereby we can increase the panel output. And can you able to see the slide 5? Okay. So can you able to see the slide 5?
Yes, sir, we can see that.
Okay. So the the renewable energy integration is getting a research attention. So we can either you can integrate with solar collectors, thermal collectors, or solar photovoltaic collectors, especially in the climatic conditions like in India, tropical climatic conditions like India. And for some cold climatic conditions, we may integrate with some other renewable energy sources like geothermal energy resources. So that so some places we can hybrid this geothermal and solar energy resources with the heat pump, because the heat, even in when we have a collaborate with research collaborations with Kazakhstan, so they have a problem with this, that is an energy resourceful country, but they are not in position to shift towards the heat pump because the heat requirement, heat produced by means of conventional methods like coal gas heating or coal gas heating, or maybe a natural gas boilers, uranium is available, oil is available, so they are very rich in energy resources. They are not in position to shift to the heat pumps. So because they have a 6 months, they have a winter. Out of the 6 months, they have a length of sunshine is very less, maybe around 7 to 8 hours, 6 hours of having effective sunshine. So they're not having a possible to get enough solar radiation to meet out to run such type of collectors. That is very difficult to promote these heat pumps in this in Kazakh market because of they are very strong in indigenous conventional energy resources. But they are not thinking about, they are not thinking about these environmental concerns, but they are thinking only about the initial investments, because the heat pumps require very huge investment, but the natural gas boilers is a portable gas boilers which may get within 100 or $200. We can get the natural gas boilers, and even get a $50 will may get a electrical resistance heaters, but they are very difficult. They are very tough to switch over to the heat pump heating systems. Even though it is a sustainable long-term option, it is having a good lot of futures, but they are not ready to shift towards this type of heating systems. But in most of the European countries, nearly it is they are totally shifted towards the heat pump heating systems. Even China is having a huge market, especially in the European countries, for the heat pumps. So that will be the scenario. So because of that, because of the less sunshine and less sunshine availability, they are integrating with geothermal heat pumps also. So we are having such type of research projects in collaboration with some universities in Kazakhstan, and also we are also done some research, and we have got some good results out of it. And and the heating moreover, the heating demand is also increasing every year. So because of increase in population, so we have to be increased. Some energy efficient heating technology should be introduced to meet out this future demand. And the lifespan of this system, it should be, we are expecting at least a 20 years lifespan. The reliability of the system should be justified to meet the at least 20 years lifetime for heat pump systems. And
so sorry to interrupt, but we've sort of exceeded 10 minutes at the moment. So we are hoping to start the question and answers in another 5 minutes or so. So
okay.
If you can wrap up by then.
So okay, just another 5 minutes. 5 to 10 minutes. I will wind up. For 10 minutes, I will wind up. Okay, 10 minutes I will wind up. Okay. So the
Sure.
yes, 10 minutes I will wind up. Okay. So, so because of the lack of standardization, most of the heat pumps, it's because based on the customer requirement, based on the demand, we are developing the heat pumps, but it is not standardized like other products in the market. So these are some of the factors which has influenced this global market, and the cost, availability. So these are the lack of working fluids. Yes, this is a major problem. The lack of working fluids, because presently using working fluids like R134A, R410A, R32, and these are the refrigerants which are commonly using in heat pumps. These fluids are completely phased out according to the Paris Protocol 2016. So according to this, the refrigerants with the global warming potential less than 150 are recommended for its usage. So none of the existing fluids are going to be sustained in future. So it is very essential to identify some energy efficient and environmental working fluids. So olefins have been introduced. So recently the olefins have been introduced to meet the requirements for the heat pumps, but the olefins, again, it will be a problem of a format because of its low global warming potential of around 4 or 5. It has been introduced as an option to replace the existing R134A and R134A, but the problem is this olefin is having a major problem of fast decomposition, and it will form the problem of trifluoroacetic acids. TFA is the major problem with R1234YF or R1233ZE. So these type of refrigerants, these olefins, having a lot of advantages that there. So it is having a lot of advantages with respect to its operating temperature, with respect to its critical properties, thermodynamic properties, with reference to its thermophysical characteristics. It's well and good, but the problem is this type of working fluids cannot be used according to the Kyoto Protocol. Sorry, according to the Paris Protocol 2016. So even though it is having a low global warming, the fast decomposition of such working fluids, fluids in the atmosphere is an unsaturated hydrochlorofluorocarbon or unsaturated hydrofluorocarbon. So fast decomposition makes to create a sudden impact on the environment, so which will be not good. So you have to be faced with these refrigerants also soon. So only option is carbon dioxide, but the carbon dioxide is having a major problem of its low critical temperature and its high operating pressure. These are the major problems which will be going to use it in heat pumps. But when we are going to use with carbon dioxide, or maybe for a or a propane or a R290, there is a propane or some propylene R1290. So such, if you are going to for such type of refrigerants, then we have to be very taken care. When we are going for a carbon dioxide, it's very essential to have the very strong system to withstand the high operating pressure. And we are going for a 290 propane or propylene, so R1270. So our R1270, if we can go for these refrigerants, we have to be taken care about the flammability issues. So these are the major drawbacks which we are going to face in future when we are going to identify working fluids. Because now China has introduced a new refrigerants, R1233ZE. There is a refrigerant which is going to work up to 150 degrees centigrade, So, R140 plus degrees centigrade, it is possible to use. So if we can go for such type of refrigerants, we can extend the range of operating temperature, but we cannot expect to be an environment friendly. So such refrigerants will have some problems with respect to its ODP as well as global warming potential. So because it is an unsaturated compound, it contains chlorine as well as fluorine. So the sudden decomposition will create the immediate environmental impact. So this will be another series issue which we are going to. But the Chinese they introduced this refrigerant compounds, but it is not going to be a sustained option for a long time. So we have to be, it's an interim option. So the identifying a proper refrigerant for a heat pump, that itself is a major task which you're going to face it in future. For a small capacity heat pumps with around less than 10 kilowatt, then we can recommend for propane as a good option. It's a hydrocarbon. Being a hydrocarbon, the consumption of less than 10 kilowatt may require around around 1 kg. So the 1 kg of use of 1 kg propane when in a heat pump, when the heat pump is installed in an open atmosphere, will not make any flammable risk. For producing during its operation. So that will be another thing, and lack of awareness is another problem. So it is very difficult. So about the lack of awareness, even many industries, the industrial persons there doesn't have an awareness. Even in our location in Coimbatore region, they are not understanding the meaning of heat pump and why they are how we can use the heat pumps, that are not having that much awareness. So this all leads to, even for a dishwasher application also, there are even small application also for a small food equipment applications. They are using resistance water heaters. Wherever the possibility we are using heating systems, resistance heating systems, it is possible to replace with a energy efficient heating system. There is a heat pump heating systems, then it is possible to have significant energy savings. So even in some washing machines, then most of the washing machine manufacturers, that shifted their drying system to the heat pump drying systems. So these are some of the latest changes that are happening, but it should be we have to create awareness to the people, so that heat pump is an energy efficient system which will produce efficient heating when comparing to the electrical resistance, and it having a less carbon emissions when comparing to the electrical resistance heating systems. So this awareness, it should be reached to everyone, so that we have to be switched over to the heat pumps. So, and it's having a lot of challenges in retrofitting of the systems. So I'm not going to have, these are the major things. And energy source availability, maintenance, repairs. So these are the following research tasks. I'm going to give a very few things shortly. So the cycle modifications. So even after implementing, there is a lot of scope for improve its performance of vapor compression refrigeration cycles. We can make some modifications in the compression refrigeration cycle, so that we can improve its performance. So when we need a temperature more than 50-degree temperature lift, it is better to go for two-stage options, either the two-stage with a single fluid or two-stage with two different cascade arrangements, or otherwise we can integrate with the renewable energy resources, either we can identify a suitable working fluids to meet out their requirements, or we can improve the standardization to meet our global requirements. Okay. So these are some challenges in the heat pump market, and I'm going to rush up these slides because just these are some of the things. So these are the refrigerants in the transition is. Can you able to see the slide change? Hello.
Yes, sir.
Can you able? Yeah. Okay.
Yes.
So these are some of the refrigerants which is commonly using in heat pump systems. The earlier CFC, then it is shifted to CFC, and HFCs are shifted to HFC refrigerants. HFC refrigerants are shifted to the hydrocarbon refrigerants. Hydrocarbon are hydrofluoroolefin, carbon dioxide, and mixers, and hydrocarbon mixers. So it is shifted like this, but these hydrofluorocarbons are the interim options, but we are going to phase out soon.
So sorry to interrupt again.
Just 2 minutes, madam. Just 2 minutes. So these are the environmental protocols which restricts the use of working fluids. So these are some of the heat pumps were developed in our laboratory for the various applications. developed a photovoltaic integrated heat pump for producing the electricity. We are utilizing the evaporator for producing the cooling arrangement. This for photovoltaic panels. This is utilized for power this compressor. So this is a two-stage cascade heating system we have developed for in Kazakhstan to meet the space heating requirement extreme cold climatic conditions of around -20°C.
The slide.
Yes.
You'll need to change the slide.
Just a minute, madam. Just a minute.
We are at slide 5 right now.
Okay.
We can see the slide 19 right now.
Now it's okay. 17.
Yes, 17 is visible.
Okay. Is 18? It's okay.
Yes.
So these are some of the research contributions in the field of heat pumps. Now I'm 19 for the drying, this is for greenhouse heating, and this is for some with heat storage, and for desalination. This is for now I'm in slide number 21, and this is for water heating heat pumps. This is for with cooling of photovoltaic panels.
So we can't see the slide 21 yet. We are on slide 17 right now.
So, now it's okay, madam.
Visible, yes.
Yes, this is a photovoltaic panel integrated system as part of our research projects we have done. This is regarding the space heating heat pumps, which has been developed in Kazakhstan for space heating requirement of around from -20 to +40°C. Two-stage cascade heat pump we have developed for producing the hot water. From there, it will be utilized for running the radiator heating systems. And also, sorry. So these are the systems we are developed out of my research interest. Okay, madam. Thank you. Thank you for providing the opportunity to share some of my research experience in the field of heat pumps, especially in the drying, water heating, space heating, and desalination applications. Thank you.
Thank you so much, sir, for the wonderful presentation. So, like, it's already 3:53, and a lot of questions are there in the chat box. So,
yes.
Like, we can take the questions for up to like 4. So we have 7 minutes. I will try to take the questions as much as possible, and we will post you for the speakers. Then they can reply back, and we will forward the responses. So here comes to the first question, and it is about some refrigerants R134A, R407C has GWP value of approximately 1350. So how do you see impact of these F gases on environment while decarbonization? These F gases contains PFAS substance which has emerging risk on health. So this question is Mr. from Prashant Gupta, and
so can I answer for this question, sir?
Yes, sir. Please.
Okay. So this R134A is a tetrafluoroethane. It's having a fluorine, having more 4 atoms of fluorine. When it is when it is emitted in the atmosphere, it will capable of absorbing more amount of reflected radiations, and it will enhance the global temperature highly. So because of this, it should be phased out. According to the Kyoto Protocol 1997, these greenhouse gases should be phased out soon. So after this, the hydrocarbons have been, hydrofluoroolefins have been in picture. So hydrofluoroolefins is recommended as an alternative option to R134A. But hydrofluoroolefins moreover, the hydrofluoroolefins have been proved as having a similar thermophysical properties, similar thermodynamic properties, and it is having it is a best option with global warming potential of less than 4. It's around 4. They're saying it's around 4 is a best option to replace R134A. But the problem is now again the problem lies with phase out of R134A with R1234IF. The reason is Now they are identified this R1234YF is having a short lifetime, and it is an unsaturated hydrofluorocarbon decomposed fastly, and it create more environmental impact, and it create more environmental impact immediately when comparing to R134A. So R134A will give late impact, whereas it will give sudden impact. So that will be not good for the replacement, but it may be considered as an interim option. And the people that start thinking towards the hydrocarbons. So hydrocarbons or R290 is a best option to use it in a small heat pumps. For a big size, it is better to go for carbon dioxide based working fluids. For example, for a medium temperature applications, again, the condenser cannot be used. We have to go for a gas cooler. We can go for a carbon dioxide. We need it's working on a transcritical cycle. So partially it is below this critical, partially above the critical. So above the critical means we need to go for a gas cooler. This will be another big challenge. So to go for such type of modifications. So for replacing R134A with 290, not pure 290, with 290 R600 blend, that is a best option right now. For a new systems, it is better to go for R290, pure R290, propane systems.
Yes, thank you, sir, for answering the question. Can you stop sharing your screen, sir? And
yes. So
the next question is from Mr. Prasenjit Singha, and he is asking that while generating the heat through using the heat pumps, cooling will be a byproduct. So how can we utilize that cooling, and how can we like you both we can use heating and cooling? So Mr. Hemant, would you like
yes, sir, can I answer for you? Yes.
Yes, sir, you go ahead.
So the thing is, so we can't expect the heating and cooling demand simultaneously. Sometimes you may require heating, sometimes you may require cooling. In such cases, whenever the heating is required, the cooling energy can be stored or dumped in somewhere in a storage tank, and whenever it required, we can utilize it. So we require a big storage tank to store the cooling energy. Whenever there is a cooling energy is required, we can utilize the cooling energy and we can dump the heat energy in the another storage tank. But it's an investment is more. Or otherwise, if we can use it for exclusively for a heating applications alone, but there is no need of cooling application, we may utilize it to cool the photovoltaic panels, because during summer the photovoltaic power generation may be the efficiency of the photovoltaic power generation maybe comes down. So we may integrate with some photovoltaic panels. The cooling coils may be integrating with some photovoltaic panels to utilize the cooling effect effectively. Thereby we can generate some amount of electricity generation in an efficient way. That may be integrated with some grid. Integrate with grid. From the grid we can tap the electricity at free of cost, or accordingly we can compensate the power consumption based on the electricity board conditions.
Just to add it to Professor's thing, there are so many applications, there are so many industries requires a simultaneous heating as well as the cooling. For example, AHU application. In the AHU application, the cooling will never be zero in majority of the tropical conditions and all. Okay, so cooling is required irrespective of whatever the things and all. So cooling and heating will happen simultaneously. For those applications, then we can directly use the cooling as well as the heating simultaneously.
Yeah, even in a case of a hotel, I suggest in a hotel, they're using electric heaters for producing the hot water for washing hand for domestic sanitary application, and they are utilizing an air conditioner at the one floor, and they are utilizing the hot water heaters in the another place. We can integrate these two. If we can integrate the air conditioner with that hot water generation units, so that we can save some amount of energy in that place also.
Hotel generally, except the north in India, balance all the places. Even minimum cooling load is always going to be there. So with the help of heat pump, even you can reduce those cooling loads, or during that time you can even avoid the running of the chiller.
Yes, yes, sir.
Yes, we do have a lot of questions coming in, as I see in the chat box, but due to the time paucity, we will just be able to take one more. And Hemant, if you would like to answer this question, and then after we will wrap up, because we have actually sort of exceeded half an hour.
Yes.
So this question is coming from Jnaneshwar Shirsagar. He asks, industrial residential heat pump design selection, is pinch analysis compulsory?
Pinch analysis is not compulsory. Wherever there is a multiple source and multiple sinks are available, only for those areas we should use the pinch. And for the simple domestics and all, that much of actually it is not a complex network. During that time, simple feasibility study itself will be sufficient to give the solution. It can be done, but it is not required. So it is actually like a overactivity.
Yes, I hope it answers your question, Jnaneshwar. Thank you so much for being a part of this webinar. We will try to share the mail IDs of the speakers with everyone so that you can directly connect with them. We can also circulate their LinkedIn IDs if they're okay to connect with everybody and then subsequently answer queries. Again, thank you so much to the speakers for sharing their insights and creating this very valuable round of discussion. Thank you so much. And we'll share the recording with everybody soon. Please also keep an eye out for the next webinar. Please keep an eye out for your mailbox and the new details that we'll be sending on.
Thank you, sir. Thank you very much. Thanks all.
Thank you, sir. Thank you for the opportunity. See you.